Well, good morning, everybody, and welcome to our last day of new material for this unit. Today, we are going to take a look at the calendar, get a sense of where we're at, and actually, we're going to even talk about how we are going to wrap up second quarter together. Then we will take a couple minutes and we will get oriented to the resources and materials that you'll have for the day. And then we're going to get started and we're going to talk about molecular geometries. So let's look at the calendar and let's take a look at how these next couple days are going to play out. So as I mentioned, for the next 2 days, we are going to be, well, for the next class period, but 2 days for me, we're going to be looking at molecular geometries. Last time in class, you learned to draw Lewis dot molecular structures, and what you're going to find out is that these structures actually have really interesting three-dimensional properties, and we're going to talk about those today. This will then be foundational to what you're going to do in lab next time. We will actually be working not in lab itself, but we will be doing a lab, the last lab for second quarter, where you will be working with your lab partner and you'll be building the models. You'll actually be getting the ball and stick kits and you'll be building models for the molecules that we've been talking about and we'll continue to talk about for the next couple days. Notice then that this leads us to the test, which will be the next and last test, of course, for second quarter. So let's talk about some deadlines. So the homework that you did last time, the Lewis dot molecular structures assignment, that, of course, as is always the case, is due today. By midnight on whichever particular day is yours, be it an A day or a B day. So do be sure to turn those assignments in before midnight tonight. Then the geometries homework that you will be working on as a result of what we're about to do will then be due on the day of the lab. Again, if you have questions about any of this, some of you have already, I hope, found success emailing me. It's really been fun to sort of think through things with people. I trust that if you're not emailing me, you're reaching out to Ms. Call and that you're getting the support that you need as you engage in learning this material. Then, guys, the molecules lab will be due the day of the test. And you should also know then that on the 11th, this will actually be the quarter 2 deadline for late work. And that will be at 1 p.m. Remember that the day of the test is the cutoff for turning in any late homework. So if you're an A-day student, your late homework, of course, will be due at midnight the day of the test. And then, guys, if you are in a B-day class, then, of course, your homework deadline will be the 11th at midnight. But in addition to that, this is the end of the quarter, not for the school, but for us. And so by 1 o'clock on the 11th, you need to turn in all of your late lab work or activities. Remember, lab work and activities are handled differently than homework, and these things are due at the end of the quarter, which again for us will be on the 11th. Now, the good news, at least for me, is that I'm out of quarantine on the 9th. So I'll be around to be with you while you take the test and also be there to be gathering up your late labs and activities work as we move into the end of the quarter. So guys, that'll wrap us up. When you're done with the test, if you're caught up, you will have done everything for second quarter's grade. We'll talk about what the following week, the last week of the calendar year, is going to look like. But understand that anything that we do there will go on your third quarter grade. So if you're all caught up, you are done with the quarter. Understand that if you do need to do remediation for this test, that there will be time to do that before we finish up the quarter or the calendar year on the 18th. Okay, so guys, those are the calendar things that I wanted to talk with you about. Let's take a look now at what we are doing today. So to get started, let me go here, let me get this going. And guys, today what we're going to do is we're going to talk about molecular geometry. To get you started on this, you should have in front of you a copy of something that looks surprisingly like this. This is your notes page for today, and you'll notice that it's double-sided, and I'd like to orient you to this before we talk about the big idea of what we're going to do today. So looking at the front of this page, guys, you'll see that there are actually two terms that we need to talk about in order for you to be ready to learn the interesting things that we're going to do today. You need to learn about the idea of electron domains, and then you also need to learn about something called VSEPR theory, and we'll cover that in just a minute. Now, relative to VSEPR theory and electron domains, there's then a concept down at the bottom of the front of this page that we'll share with you as well, and this will then provide the foundation that you will need in order to switch on to the back of this page. Now guys, looking at the back of this page, you'll notice that it's organized into tables, and anytime you see tables, you should be thinking about an organizational structure that brings ideas together in repeated ways. But then you'll also notice that these tables are broken into sections, and there are 3 of those sections. And if you look at the heading of these sections, you will notice that it says 4 electron domains, 3 electron domains, and 2 electron domains. Now, granted, you don't know what electron domains are yet, but what you're going to find out is that the way to organize your thinking about these molecular geometries is to organize them by the number of domains. And notice that we will talk about an ever-decreasing number of domains, 4, 3, and 2 domains. When, guys, we're done filling out the back of this, we will then get really practical and we'll talk about what you need to be able to do as a result of this. So, guys, with that foundation set, if anything comes up on the slides that is not included on this notes page, you don't need to worry about writing it down. These are the critical components. So, with that said, let's take a look back at your homework. So guys, this is a page lifted straight out of the Lewis dot molecular structure assignment that you did. And the reason that I bring this up is because this provides a common ground where we can talk about what we're going to do today. So guys, looking at these Lewis dot structures. First of all, if we look at this Lewis dot structure for NO2, and if we look at what we've drawn, which is absolutely fine, this is correct, guys, you'll notice that as we look at these, it appears as if this angle around the nitrogen is 180 degrees. And if we were to look at this, we might imagine that this molecule in real life is all in a line, and you've got a nitrogen with an oxygen stuck on each side, and the molecule looks something like this. Well, what you're going to find out is that is absolutely not the case. This molecule is much more complex and interesting than that. And by the end of the day, you're going to be able to figure out what this looks like. Now, similarly, taking a look at NO3, this looks like a 180 degree angle. These look like 90 degree angles. And we might imagine that that molecule kind of looks like that. Well, it turns out, not surprisingly, that's not the case either. And you're going to find out that all of the angles in this molecule are actually 120 degree angles. And drawn more appropriately, the molecule would look like this without its unshared pairs of electrons. Then looking down at the last example here, of course, this looks like these are all 90 degree angles, and I think by now you're probably catching on to the idea that it's not going to be 90 degree angles. You're going to find out in a couple minutes that these are 109.5 degree angles, and that this thing does not look anything like its Lewis dot structure. So guys, with that said, you might be looking at this and you might be asking yourself, then why do we do Lewis dot structures in the first place if they aren't actually accurate? Well, and guys, the answer is it's not that they're inaccurate, it's just that they don't provide us information about the 3-dimensional structure of these molecules. But they do definitely provide us information. So let's talk. So guys, to this point, we have drawn the 2-dimensional Lewis dot structures for molecules. And you know what? These have lots of great purpose. Lewis dot structures do a really good job of telling us the order that these elements bond in. It does a great job of telling us the types of bonds they form, but it doesn't tell us anything about the three-dimensional structure of these molecules. And guys, that's what we're going to do today. We are going to step, if you will, off of the paper, and we're going to push our study of these molecules into 3 dimensions. And we'll be talking about this conceptually and visually today. And then next time in lab, you'll actually get your hands dirty and you'll be building these yourselves. Now, in order to do this, what we've got to do, and this is where we turn to the front of your notes page, we need to talk about 2 terms and a concept. So with that said, grab your notes page and let's get started. So the first term that we need to talk about are what are called electron domains. And you'll notice that there's space in your notes to write down some definitions. So let's do that. So guys, an electron domain is simply defined as the space that electrons occupy around the nucleus of an atom. So in the same way that if we're a biologist and we talk about the domain of a mountain lion, we think about the place where mountain lions live. When we talk about electron domains, we're talking about the places that electrons live. Now, the interesting thing is you already know about these. We call them orbitals. Well, they're related. The difference is that it doesn't matter how many electrons are in a domain, it still counts as it still counts as one domain. And in the same way that if you have 3 or 4 or 5 mountain lions living in the same area, we still call that one domain. If you have 1 or 2 or 3 or 4, 5, 6 electrons in a domain, that still counts as one domain. So how does that work? Well, the answer is that there's generally 2 types of domains. We have what are called bonding domains, and we have non-bonding domains. And you'll notice that this is presented in your notes there. So let's talk about them individually. So bonding domains are any shared pair of electrons. But here's the twist from what you learned last time. Any bond type counts as one domain. And we'll look at more at that in a second. So domains are the places that electrons occupy. They can be bonding or non-bonding. But relative to what you learned last time where you were counting shared pairs and lone pairs, these bonding domains are the shared pairs, but any number of shared pairs counts as one domain. Then there are also what are called non-bonding domains, and these are the lone pairs. So let's take a look. You'll notice that there's a place in your notes to draw this picture. I think it would be worth doing. So talking about electron domains, there are actually 4 things that count as electron domains, and each of these alone counts as one domain. So a lone pair, that counts as one domain. A single bond, that counts as one domain. A double bond, that counts as one domain. And then a triple bond also counts as one domain. So with this in mind, the question then becomes, what do you need to be able to do with this idea of electron domains? And the answer is, you simply need to be able to count them. So let me pause for a second, give you the opportunity to catch up in drawing your domains. And then guys, the next thing that comes up, please don't try to draw it. Just tune in and let's make sure you're clear on this. Okay, so here we go. Take, for example, the molecule that you drew in your Lewis dot homework. And again, guys, if you didn't pick this up by looking at the answers at the front of the classroom, guys, this is the only molecule that you have to memorize. There are multiple ways that you can put CH3COOH together. You probably wrestled with this a little bit as you were working on the homework last time. But guys, understand, this molecule you have to memorize. It's the only one that you do, but you need to know this one straight out. We'll talk more about why that's the case later. But using this as our example, let's now focus on some of these atoms. So for example, we look at this carbon. And the question that you need to be able to answer is, how many domains are around this carbon? So give that a thought for a second. How many domains are around that carbon? Now that you've had a chance to think about it, let's count. So we have a single bond, one domain. Another single bond, another domain, another single bond, another domain, and a fourth single bond is a fourth domain. So there are 4 domains around that carbon atom. So now let's take a look at this carbon atom. Same question. How many domains are around that carbon, the one on the right? Give it some thought. Okay, so now let's take a look. So we have a single bond here, which is one domain. We have a single bond here, which is one domain. And then we have a double bond here, which is, surprisingly, one domain. Again, yes, it's 2 shared pairs. It's a double bond, but it is one domain. This is one space where electrons can be found. That means that this carbon has a total of 3 domains. Okay, so I know that that was probably maybe a little surprising, but let's keep going. Let's take a look at this oxygen. Again, the same question. How many domains surround this oxygen? Well, we've established that single bonds count as one domain, so there's 2. But now what about these unshared electrons? Well, this is a domain, a place we find electrons, and this is a domain, again, a place we find electrons. That gives us 4 electron domains. All right, let's do one more. The last one that I'd like to look at with you is this oxygen up here at the top. Let's pull together some of the things that we've refined looking at these other atoms, and let's ask the same question. How many domains on that oxygen? Well, let's count. So we know that a unshared, a lone pair of electrons is a domain, so that's 1. Here's another lone pair of electrons, that's 2. And then here is a third domain. Again, it's a double bond, but it is a third domain. So this oxygen then would have 3 domains on it. 2 lone pairs and a double bond for a total of 3 domains. Okay, so now that we've taken a minute and we've talked about how to identify and count electron domains, let's move on and let's talk about an important idea called VSEPR theory. Not surprisingly, VSEPR is an acronym, so let's just get it on the table. What does VSEPR theory mean? And guys, VSEPR theory stands for the valence shell electron pair repulsion theory. So let me give you a chance to write that down. Again, valence shell electron pair repulsion theory. Now guys, I know that those are a lot of perhaps big words, but if we spend a second and tear this apart, I think you're going to find that this makes a ton of sense. So let's try this. So where are the valence electrons? Well, the valence electrons are on the outside. And when these valence electrons get together in pairs, we call those pairs or groups of pairs domains. So the valence shell electron pairs are the domains. Well, what do? The answer is they repel. Because we're talking about electrons, we understand that electrons are all negative and like charges repel. And as a result, guys, all the VSEPR theory says is simply this. It simply says that electron domains repel each other. I know that doesn't seem earth-shaking because you've been introduced to these ideas throughout this unit, but you're going to find out that this has a very important implication, and it's this. This repulsion causes these domains to get as far away from each other as they possibly can. And this is what leads to their interesting 3-dimensional shapes. So we need to keep in mind that these Lewis dot structures, these molecules, are not flat many times. They're not as simple as they first appear because all of these bonding and non-bonding domains push on each other and they push these molecules into interesting three-dimensional shapes. Okay, so one last thing to cover in terms of building background, and then we're going to move forward. So here's where we are. We know that electron domains are the spaces that electrons can occupy, and we now know that these domains push on each other. The last thing that we need to talk about is that not all of these domains are the same size. So let's look at bonding domains first. Now guys, when we think about bonding domains are long and skinny. The reason that they are long and skinny is because they're being pulled on by the nuclei of the two atoms that are involved in the bond. And I know I skipped through that quickly. Take a second, catch up with me in your notes, and then let's take a look at what we're talking about. So again, electron domains are not the same size. Bonding domains are long and skinny. The reason is because they're being pulled on by two nuclei. So what does this look like? Well, it looks like this. So here we have an atom, and over here we have an atom, and these two atoms are bonded together, and this nucleus, that doesn't show up very well, does it? And this nucleus is positive, and this nucleus is positive, and these two positive nuclei pull on this cloud of electrons, and it stretches it out, and we end up with a long, skinny bonding electron pair. Notice that this looks like a cloud because, in fact, we are talking about shared clouds because we understand that electrons occupy spaces that look more like clouds. Okay, so what about non-bonding domains? Well, not surprisingly, these are short and fat. The reason that they're short and fat is because they are only being pulled on by one nuclei. They're non-bonding, which means they're not involved in a bond, so there is not a second nucleus tugging at this electron cloud. So again, let me give you a second to catch up, and then let's take a look at what this looks like. Okay, so this then is what a non-bonding electron pair looks like. Notice over here, we've got the nucleus of the atom, and then this is an electron domain, but notice that this electron domain is only being pulled in one direction. Because it's only being pulled in one direction, this cloud of electrons puddles, it gets, well, short and fat, and it occupies more volume around the nucleus of the atom. Okay, so now you're looking at this and you're going, okay, I understand that bonding domains are long and thin and that non-bonding domains are short and fat, but what does that have to do with molecules? Well, guys, let's look at a molecule. For example, a water molecule. Well, if we look at a water molecule, we understand that as we learned before, this has got 2 bonding domains, and it's got 2, well, non-bonding domains. In the last homework, we called them shared and lone pairs, but in this case, we're going to use the new term, and so we've got 2 bonding domains and 2 non-bonding domains. But what do those domains actually look like? Well, let's look at the bonding domains first. So this line, we remember, represents 2 electrons, a shared pair of electrons. Well, what does that look like? Well, we just learned it looks like this. It is a long, skinny, shared pair or bonding domain. And the same is true of this domain down here. We've got another long and thin bonding domain. So what about the other domains? What about this guy and this guy, which are non-bonding domains? Well, these domains, as we know, they're non-bonding domains. They're lone pairs, and as a result, they're only being pulled on by the nucleus of the oxygen, and therefore they look like this. They are short and fat. So the question then becomes, what does that do to the molecule? Well, remember, these things VSEPR. these things all start to push on each other. And what you're going to find out is that these big, fat, non-bonding domains take up more space, and they push more on these bonding domains than the bonding domains push on each other. The bonding domains are long and thin, don't take up a lot of space, don't give a lot of push. These non-bonding domains are big and fat, and they push a lot on these bonding domains, and they change the structure of these molecules. Okay, so guys, let's take a second and pause, and let's make sure that we're all ready to flip this page over and start thinking three-dimensionally. So here's where we are. We talked about bonding domains. We understand that, we talked about domains in general. We talked about the idea that domains are the spaces that electrons occupy. Those can be bonding domains, which is a single, a double, or a triple bond, one domain, and then lone pairs, which also count as one domain. Then we learned that these domains push on each other. And the last thing that we learned is that non-bonding domains are short and fat, and that bonding domains are long and thin. Okay, so with that as background, we are now ready to flip this page over, and let's start moving into 3 dimensions. So guys, in order to move into the 3rd dimension, what we've got to do is we've got to step out of 2-dimensional space. We understand that when we draw Lewis dot structures, they tend to be flat. Because our paper's flat. But what we need to do is begin to visualize these molecules in 3 dimensions. So let me help you with that. Please don't write down this question, but I would like you to write down the answer. So what we're going to do is we are going to now talk about molecules that have central atoms with 4 electron domains. So here we go. Building the concept, think about this question. When 4 objects surround a central point, in this case our central point will be the central atom, now in 3-dimensional space, what angles are created if these objects are as far apart as possible? And guys, why do we talk about them being as far apart as possible? Well, that's the valence shell electron pair repulsion theory. They get as far away from each other as possible. So if you're not visualizing what we're talking about, let me offer you this. Here we have a central point. That red dot is our central point. If this were a molecule, that would be our central atom. Now what we're going to do is we are going to spread 4 points, domains, but in a minute, 4 points around the central point. So here we go. There's point number 1. Then we'll place point number 2 on the right. Those are as far apart as possible. Then to continue to spread those out, point 3 could be here, point 4 could be there, and that would spread these out as much as possible. The question then becomes, what angle is created when we do this? Well, let's draw in some lines connecting our points, and we do this. And I think that most of you from your math background would look at this and you would say, oh, those are all right angles or 90-degree angles. So it would appear that the answer to this question is 90 degrees. But I hope that some of you are looking at this and going, wait a minute, this drawing actually doesn't have anything to do with the question. If the question were about 2-dimensional space, then the answer would be 90 degrees. But now we need to talk about 3-dimensional space. And when we talk about 3-dimensional space, these blue points can move literally off of the paper. And when they do, what angles are created when they spread out as much as they can in 3-dimensional space? Well, in order to show you this, we need a tool that allows us to think in 3 dimensions. This is that tool. You'll notice that I can grab this and I can move it and I can show you different orientations to this. If you would like to get to this, this is actually a resource that is linked in the on the lab day next week, and it is the tool that you'll be using instead of the model kits if you end up needing to do the makeup lab. Okay, so here we go. Obviously, this is not set up to answer our question because right now we have, let me switch colors, we have a central point and then we have 2 points surrounding it. We need 4 points. So let's add some more points. So there's 3 points and there's 4 points. All right, so now we're getting closer to the answer. So let's drag this around and let's get a look at this in 3-dimensional space. So looking at this molecule in 3-dimensional space, if nothing else, I hope that you can now see that this is not, these are not 90-degree angles. If you're not sure what I'm looking at, let's try this. So here would be a 90-degree angle. And you'll notice that none of these other domains sit along that line in this molecule. So hopefully you can not only look at this and see that it's not 90 degrees, but also see that it's greater than 90 degrees. So the question then becomes, what are these angles that are formed within this molecule? And interestingly, guys, the answer to this is 109.5 degree angles. So not only do we need to know the angles, we also need to know the name of this molecule. And you'll notice that we've got 1, 2, 3, 4 points surrounding that central point. And many of you probably know that the geometric term for 4 can be quad or tetra. And we use the tetra term, and what we have now created is a structure with 109.5 degree angles, and we call this tetrahedral. So what we now understand is that anytime we have a molecule that has 4 domains on the central atom, the angles that are initially formed in that molecule will be 109.5 degrees, and we call this tetrahedral. Now here's where this gets interesting, because it turns out that that doesn't mean that the molecules that are created by this 4-domain structure are also tetrahedral. The reason is because not all domains are bonding domains. So guys, let's do this. I know that thought was confusing, but watch. Jump down here into your table and do this with me if you would, please. These are the molecules that we are going to look at. Let me see if I can zoom into this for you. I think I can. Oh, good. Okay. So guys, what I need you to do is take a look at CH4, NH3, H2O, our good friend water, and then HF. These are going to be our examples of molecules, all of which have 4 electron domains. But with that said, let's take a look at their Lewis dot structures. Now guys, I chose these 4 molecules because you drew their Lewis dot structures in the previous homework, the Lewis dot homework. So let me just give them to you. CH4 looks like this. Take a second and scratch it down. NH3 looks like this. And guys, I would strongly encourage you to draw this like I am. I know that you know that that lone pair of electrons could be top, bottom, left, right. But I think you'll find this easier if you draw them like I do. So now let's take a look at water. H2O looks like this. And then finally HF, like so. I'll zoom back into this in a second, but I need my writing tools, so let me grab that, and then let me zoom back in for you so you can get these drawn. Give you another second or two to draw these structures, and then we'll dig in and talk about them. Okay, these are probably familiar enough to you that you were able to get them on the paper fairly quickly. So the first thing we need to talk about is, what do all of these structures have in common? And the answer is not hydrogen. So let's take a look. Well, looking at CH4, that was a mess. We've got 1, 2, 3, 4 domains. This is not working well zoomed in. Let me start over. So we've got 1, 2, 3, 4 domains. Looking at NH3, 1, 2, 3, 4 domains. Looking at H2O, 1, 2, 3, 4 domains. Looking at HF, 1, 2, 3, 4 domains. So guys, the thing that all of these molecules have in common is they all have 4 domains. So now let's work to the right and let's take a look at how these molecules are different. Well, looking at CH4, that's got 4 bonding domains. As a result, it has no non-bonding domains. The question then becomes, what does this molecule look like and what is its molecular geometry? Notice that its domain geometry is tetrahedral. But what about its molecular geometry? What does the molecule look like, and what is the actual angle in the molecule? Well, guys, to answer that question, let's jump over here and let's take a look at a model of this molecule. So this is actually CH4. This is our C. Each one of these represents a hydrogen atom. And guys, looking at this CH4 molecule, you'll notice that this is our example of something that is tetrahedral. We've got a tetrahedral structure. We've already identified this as having 109.5 degree angles. And so guys, as a result, the angles are 109.5 and this is tetrahedral. So now you're going, wait a minute. Of course it is, because we already looked at that example of 4 points. Well, guys, go to the next one with me. Here we go. Now we've got NH3. How's it different? Well, guys, count the bonding domains. There's only 3. And there's 1 non-bonding domain. So the question then becomes, what does this molecule look like? Well, guys, in order to show you, I'm going to pull everything off of this molecule, and I'm going to put 1, 2, 3 bonding domains around that central atom. But then, guys, watch. An unbonded pair of electrons, this non-bonding domain. And we'll orient this so this is on the top. So, guys, you can see that this is no longer tetrahedral. It doesn't look like a tetrahedron at all. It doesn't have this 4th bond. Yeah, it's got an unbonded pair of electrons here, but remember, that's a cloud. It's a probability. So in all reality, all this molecule has, let me move it so we can see, all this molecule has is 3 points surrounding the central atom. So the question then becomes, what are these angles? And what do we call this thing? Well, guys, first of all, we need to talk. This angle, and then the angle behind this angle, these all started out as 109.5 degree angles. But the trick is this. This big, fat, unbonded pair of electrons pushes like crazy on these bonded pairs. And when it does, it makes this angle smaller. How much smaller? You don't actually need to know. The answer is 2.5 degrees, but it closes that angle down by 2.5 degrees. All that you need to know is that that angle is less than 109.5. So now the question is, what are we going to call this? Because it's not a tetrahedron anymore. It doesn't look like a tetrahedron. But what we actually have is a pyramid. We now have a pyramid that actually has 3 points on its base. So we have a 3-footed pyramid. The name of that is then the name of the molecule. So we're less than 109.5 degrees, and the name of that 3-footed pyramid is what we call trigonal pyramid. Okay, so let's continue on then. So getting this idea that just because a molecule has 4 domains doesn't mean that it's always a tetrahedral structure as a molecule, let's take a look at water. So again, how many bonding domains in water? Of course, there's 2. How many non-bonding domains in water? Also 2. So then the question becomes, what does this look like? Well, again, let's clean up our mess. Let's put 2 bonding domains on this guy, but don't forget 2 non-bonding domains on this guy. And so as we rotate this, let me find an orient. Oh, hey, that's actually pretty good. As we take a look at this structure, you'll notice, guys, that actually in space, we only have 2 points in space. These domains are there. These non-bonding domains are there, but they're clouds. They don't actually identify a plane. So what are we going to call this thing, and what are the angles? Well, again, this angle started at 109.5, but now we've got 2 big, fat, unbonded pairs of electrons pushing down on these bonding domains. So what does that do to the angle? Well, it makes it even smaller. It actually closes down by another 2.5 degrees. You don't need to know that. You just need to know again that it's less than 109.5. So now we need to name this thing. So guys, we've got a central point going in 2 directions. You're not going to like this, but looking at this molecule, the best way to describe it is simply as bent. This is a bent molecule. So this again would be less than 109.5, and we call this structure bent. Okay, so now let's take a look at our last molecule that has an atom with 4 electron domains. That would be HF. HF has 1 bonding domain. HF has 3 non-bonding domains. So what does that look like in 3-dimensional space? Well, let's jump over here and take a look. Let's clean this up. Let's put 1 bonding domain on this molecule, and then 1, 2, 3 non-bonding domains. So let me drag this over here. And guys, this is what we end up with. We've got our fluorine, we've got our hydrogen. So the question then becomes, what is the angle in this molecule? Guys, be careful. These are clouds. These are probabilities. These do not define points in space. So guys, we've got 1, 2 points in space. And hopefully you remember from math that 2 points do not define an angle. 2 points define a line. And because this is a line and not an angle, there is no angle. We call it undefined. So then the question is, what are we going to describe 2 atoms that are in a line? Well, the answer is linear. So this creates a structure that has no angle. We call that undefined, and we call it straight. This molecule is what we call straight. Because I know that I said linear. Actually, we'll come to that in a minute. This molecule is actually what we call straight and not linear. You'll see linear in a minute. Please don't let that confuse you. We call this molecule straight and not linear. Linear is actually the name of a structure, but we'll get to that in a minute. So this molecule is called straight. Okay, so let's review. So what we've got here is we've got 4 electron domains, molecules that have 4 electron domains. If all 4 are bonding, that's tetrahedral. If 3 are bonding, trigonal pyramid. If 2 are bonding, bent. And if 1 is bonding, we call that straight. So again, guys, the idea here is, and you don't need to write this down, but in summary, all of these have tetrahedral domain geometries because they all have 4 domains, but their molecular geometries depend on the number of bonding and non-bonding domains. So let's now move forward and let's talk about molecules that have 3 domains on the central atom. So guys, same question. When 3 objects surround a central point in 3-dimensional space, what angles are created if these objects are as far apart as possible? So here we go. Here's our picture. Here's 1, 2, 3 points. Now let's connect them with lines. So guys, looking at this, we've got a circle, 360 degrees. we've broken that into thirds, doing the math, which I know you're probably already done. These are 120-degree angles all the way around the molecule. Now, guys, the question is, what if we take this out of two-dimensional space and into three-dimensional space? And guys, the answer is it doesn't change. Even in three-dimensional space, these angles are 120-degree angles. So now we need to name this thing. And we've got 1, 2, 3 points all in the same plane. They're all in the same plane. So we call this trigonal planar. So guys, write it down and then let me show you what this looks like. So 3 objects, 3-dimensional space, 120-degree angles. We call this trigonal planar. Okay, so let's jump over and let's take a look at this 3-dimensionally. So cleaning up our mess here, 1, 2, 3 domain. Oh, too many. 1, 2, 3 domains. And this is the molecule that we create. And guys, looking at this, if I can get this, looking at this from the top, you'll notice that we can see these 120-degree angles. But when I turn this to the side, let's see if I can do this. When I turn this to the side, you'll notice that we can see that they are all in the same plane. That's where the name comes from. This is what we call trigonal planar. Okay, so same game as before. Let's now look at some molecules that have 3 electron domains and therefore trigonal planar domain geometries. These are the 2 molecules that we're going to look at. Let me zoom into these for you. We're going to look at CH2 and we're going to look at NO2 minus 1. Again, these are molecules that I've lifted straight out of your homework. So let me just give them to you. CH2, CH2O. CH2O looks like this. NO2 minus 1 looks like this. And again, guys, I would encourage you to draw this as I have. Let me give you a second to do that. Give you a couple more seconds here. Okay, now that you've had the opportunity to draw these molecules, let's look at what they have in common and let's look at how they're different. So guys, looking at CH2O, we've got 1, we've got 2, and yep, that's 3. It's not 4 because remember, double bond 1 domain. That's got 3 electron domains. Here we've got 1, we've got 2, we've got 3. These both have 3 electron domains. So how are they different? Well, looking at CH2O, we've got 3 bonding domains. Yes, one is a double bond, but we already established that's 1 domain, and no non-bonding domains. So what does this look like? Well, let's jump over here and let's build it. So the central atom there would be representative of our carbon atom. And then we've got a double bond to an oxygen. And then we've got hydrogens in both of these directions. And guys, sure enough, there it is. 120, 120, 120-degree angle. And we already know the name of that thing. It's trigonal planar. So when all of these are bonding domains, the angle's 120 and the molecular geometry is trigonal planar. And guys, maybe some of you are picking up on this. Let me let you write this down and then let's make sure you're picking up on this connection. So you'll notice that we've got 3 electron domains. All of these domains are bonding domains, and the domain geometry and the molecular geometry are the same. Because that's always the case. If all of your domains are bonding domains, the domain and molecular geometries will always be the same. So now let's take a look at NO2. Looking at NO2, we've got 1, 2 bonding domains. We've got 1 non-bonding domain. Let's take a look at what this guy looks like. Well, coming over here to clean this up, we've got a central nitrogen bonded to an oxygen, double bonded to an oxygen, single bonded to an oxygen. But then, guys, don't forget the lone pair. So here we can see our domain geometry is trigonal planar. You guys remember, this is a cloud of electron probability. It's not a thing. As a result, we actually only have 1, 2 points that define this angle. And remember, this angle started as 120 degrees, but now we've got this big, fat, unbonded pair of electrons pushing on these bonding domains. And again, this makes the angle smaller, closing it down to less than 120 degrees. So now all we got to do is name this thing. I'm guessing somebody out there is already guessing it. Guys, this is bent as well. So this structure is smaller than 120 degrees, and it's bent as well. Now, guys, you'll notice that that's as far as our table goes. And some of you may be asking yourself, well, why aren't we doing a third example where we have 1 bonding domain and 2 non-bonding domains? Maybe they don't exist. Well, guess what? They do. The reason that we're not putting it on here is because if we've only got 1 bond, then we've only got 2 things bonded together. And if that's the case, the angle is undefined and the molecule is called straight. So guys, anytime we have 1 bonding domain, it's undefined and straight. It doesn't matter what the domain geometry is. All right, so one more to look at, and this is 2 electron domains. Here we go. Same game, central point, 2 points in space, separated as much as we can. Draw the line. What's the angle? Well, guys, that's 180 degrees, isn't it? So what if we make it 3-dimensional space? Doesn't change. Guys, that angle is 180 degrees. Here then is where we talk about this being linear, because now we have these points, a central point and 2 outlying points, and these are all in a line. And this is what we call linear. Again, 2 points we call straight, 3 points we call linear. So this structure is linear. Sorry for that confusion earlier. Okay, so let's move on and let's take a look at what this looks like in 3-dimensional space. So clean this up. 1, 2 points. Grab a hold of this, and sure enough, there's our 180 degree angles, and that dude is linear. Okay, so let's jump back over here then and let's take a look at the one example we need to look at, and that's going to be carbon dioxide. You've already drawn its structure. It looks like this. Let me zoom in for you and let you scratch that down. Just like so. Okay, so now that you've had the opportunity to draw this molecule, here we go. So we've got we've got 1, 2 bonding domains. Of course, that means around the central atom we have no bonding domains, no non-bonding domains. And so let's take a look at what this looks like. Carbon double bonded to 2 oxygens. So clean this up. There's our carbon in the middle, double bond there, double bond there. Grab it and spin it. And sure enough, there's our 180 degree angles. So this molecular structure is also called linear, and it's a 180 degree angle. Again, guys, what if we add 1 and 1? Well, then that would be undefined and straight, because again, 1 bond doesn't define an angle, it defines a line. So guys, there you have it. Those are the structures that you need to know. I know that that seems like a lot of information to keep track of, but you're also going to be offered a lot of opportunities to practice, both in homework and also in the lab that we're going to do next week. But guys, do understand that through this practice, you're going to need to commit these names and angles to memory. I think that if you start looking at this page in its entirety, you'll see some patterns there that will narrow this down, because this is stuff you need to know. So here we go. Let's talk about your homework. Guys, this is what your homework is going to look like. Please don't write this down, just follow along. So this is your assignment for your homework today. It reads like this. It says, draw the Lewis dot molecular structure for the following molecules. Then identify the domain and molecular geometries and the bond angle around the central atom. So guys, how are you going to do this? Again, don't write this down, but this is the idea. Step number one, you're going to count, once you've drawn the Lewis dot structure, then you're going to count the total number of domains on the central atom. This will then allow you to find which chart you're in on the back of your notes. 4 domains, 3 domains, 2 domains. That gives you the domain geometry. Then you're going to count the number of bonding domains. This then allows you to find the line on the chart that will then give you the molecular geometry and the angle. So what I'd like to do is I'd like to step you through a few of these just to give you a sense of how this works. So guys, first of all, we're going to look at a familiar one. Let's take a look at CH2O. I'm not going to spend a lot of time explaining the Lewis dot structure, but the Lewis dot structure looks like this. So the first question then, and then what we're going to be doing is identifying the domain geometry, the molecular geometry, and the angle. So the first thing we're going to do is count domains. Let me switch colors. We'll go blue. So we have 1, 2, 3 domains. 3 domains would be trigonal planar. Now guys, be careful. You can't put TP because that could also be trigonal pyramid. So you need to write these out enough that you can tell the difference between some of these abbreviations. So the domain geometry is trigonal planar because it has 3 domains. So now what we need to do is we need to figure out the molecular geometry. Well, notice guys, it's 1, 2, 3 of these domains are bonding domains. So that then places us at the top line of the trigonal planar chart. But guys, the bottom line is this. Anytime all of the domains are bonding domains, the domain and molecular geometries will be the same. So this is also trigonal planar, and these are 120 degree, sorry, not Celsius, 120 degree angles. So there we go. So the domain geometry, trigonal planar, molecular geometry, also trigonal planar, 120 degrees. Okay, so let's take a look at the next one. The next one that we're going to look at is SiO2. The Lewis dot structure for this guy looks like this. Okay, so now let's count domains. This double bond counts as a domain. This double bond counts as a domain. So the domain geometry would be linear. Now, in order to figure out the molecular geometry and the angle, we need to know how many of these domains are bonding domains. Of course, the answer is they're both bonding domains. So the molecular geometry is also linear, and this angle is 180 degrees. Just like so. Okay, so you'll notice in the last 2 examples, the first 2 examples, all of the domains were bonding domains, and as a result, the domain and molecular geometries are the same. What if they're different? Well, N2 looks like this. So first of all, the challenge is, which one of these is our central atom? Pick one. If there's ever any confusion, we will underline the atom that should be central. But in a case like this, it's one or the other. You can't pick both. You got to commit to one. So let's say it's the one on the left. So now let's count domains. We've got a lone pair that's a domain. We've got a triple bond that's a domain. So 2 domains means the domain geometry is linear. Oops, linear. Now molecular geometry and angle. So now the question is, how many of these domains are bonding domains? Because the answer is only one. And anytime you have one bonding domain, the molecular geometry is straight and the angle is undefined. So this is an example of where we've got domains that are unbonded, and as a result, the domain and molecular geometries are not the same. So let's look at one more example. PF3. Guys, please remember when you're drawing Lewis dot structures, fill up the halogens first. Of course, I'm skipping the step of counting the total number of valence electrons. I already know it. But guys, make sure you fill those halogens first or you're going to get in trouble. So now we need to do domain, molecular geometry, and angle. So we've got 1, 2, 3, 4 domains. So the domain geometry is tetrahedral. But now guys, notice molecular geometry and angle, only 3 of these domains are bonding domains. So looking at your top table under 4 domains, and then if you find the line that indicates 3 of those domains are bonding domains, guys, this is what we call a trigonal pyramid molecular geometry. And the angle in a trigonal pyramid molecular geometry is less than 109.5 degrees. Okay, so guys, there you have it. If you need additional support, obviously I encourage you to work on this homework as quickly as you possibly can, including starting right now. Draw your Lewis dot structures well and big. Do everything that you can to make yourself successful. At first, you're certainly welcome to use your class notes in order to figure out your domain and molecular geometries and angles. But guys, quickly, you need to be able to do this without that. I would encourage you to move towards that as soon as you can. If you need help, talk with Miss Call after school. Feel free to email me as well. But guys, I think it's worth mentioning that when you take the test over this unit, you will actually be signing an integrity statement. Some of you are looking at the domain and molecular geometry information, and you're thinking this is just way more than I can ever imagine memorizing. And guys, some of you are even thinking, well, I could probably just scratch them down on a sheet of paper, bring it into the test, problem solved. Because we've had problems with this in the past, and our solution has been to have our students sign an integrity statement at the end of this test saying that they didn't do anything to compromise their integrity. It would be unfair of me to not mention this ahead of time, so guys, please understand that's going to be the case. But again, guys, dig into this. It's fascinating stuff. There's patterns. I know that you can be successful with this. So again, ask questions if you need, and look forward to doing the lab where you get to make all of this more concrete. Have a great day.